Okay, so just like 2.3 was really a continuation of 2.2, the same can be said for 2.4. Unlike 2.3 though, this section will only cover one rule, and that's called the chain rule, which is by far the most important rule when we're taking derivatives of functions. So as an introduction to discovering the chain rule, let's go ahead and take a look at this example. We have a function 3x squared plus 1 all raised to the second power, and we're being asked to find the derivative of it. So with what we know right now, the only way to take this derivative is to use the product rule. We know we can rewrite our function as 3x squared plus 1 times another 3x squared plus 1, since there are two of them, since we're squaring that function. And since we're multiplying two functions, we can use the product rule. So quick little review of the product rule. So the derivative is going to be f prime, and we'll take the derivative of the first function, which is 6x, and by the product rule we'll multiply by the second function, no derivative though, and then we'll switch those rules. And now we'll multiply by the first function, and then multiply by the derivative of the second function. And since both of our terms are exactly the same, when we add them together, there are just two of them. So it'll be 3x squared plus 1 times 6x. I'm not going to simplify that answer so that we can try to find a pattern within these derivatives, because here's the next question that we're going to try to tackle. What if the problem had been the same, but instead of squared, our function 3x squared plus 1 would have been raised to the 200th power? Well, finding that derivative would be very difficult and very long and basically impossible. So we need a method for finding the derivative of these kinds of functions so that it doesn't become a long, basically impossible problem. So since we don't know how to do this derivative, I'm going to magically make the derivative appear. So there it is. Don't worry about where it came from. I just want to do a little comparison of the derivative we took above, which we could do, and the derivative from below, which we can't do. So let's kind of compare these two derivatives. So you'll notice we have a 200 in front of our derivative, and that looks like that was maybe the original power. So that's a nice observation to see, and you can kind of see that same pattern in the one we solved above. We see a 2 in front of everything for the derivative, so maybe that was the power from the original function, the 2 right here. Okay, next we have what I'm going to call the inner function, so to speak. 3x squared plus 1 is kind of inside this power of 2, or in the second case, the power of 200. So you'll notice in both of our answers, we have that appear. Next, we can make the observation that our power is 199, and just like we did back from the power rule, it's one less than the original exponent of 200. Same can be said for the problem we solved above. There is no number written there, but of course we know that there's an invisible 1 if you want to write that in. We started off with a power of 2, and we subtracted 1 from the exponent and got a 1. So that's kind of been the process that we've known up until now. We bring the power down, we rewrite the thing that has a power. In the past it was just an x, now it's 3x squared plus 1, and then we subtract 1 from the power. But now there's this new piece at the end of both of these answers, and you'll notice a 6x for the second answer and a 6x for the first answer. Where did that 6x come from? Well, you'll notice that 6x came from the inner function. When we take the derivative of the inner function, we get 6x. So it seems like both of these problems have the same procedure, or at least their answers show something about the same procedure. And it has a little bit to do, if not a lot to do, with that power rule we studied back in 2.2. Before we get to what is called the chain rule, we got to go over a quick algebra idea, just to make sure we're all on the same page. So composite functions. Composite functions are just functions within other functions. For this particular example, I'm going to use the function x squared plus 1 all to the third power. And I'm going to call that f of g of x because there are two functions in our composite function. What are those two functions? Well, I'm going to split our example of x squared plus 1 all cubed into its two pieces, the g function and the f function. So what is the g function? Well, if you notice, g is sitting inside our f function. It's f of g of x. So the g function is whatever is inside an outer function. And in this case, g is x squared plus 1. So what is our outer function? What is the function that's containing this inner function? Well, it's a little hard to write. Maybe I could put maybe x cubed, but to avoid having an extra x in there, I'm going to just put a parentheses to the third power. That function is what's holding our inner function. I'll call g our inner function and f the outer function. When we take g and put it inside f, we get the original function, x squared plus 1, all to the third power. And what that brings us to is the chain rule. It's a technique for taking derivatives of these composite functions. So let's take a look at the chain rule. You'll notice in the chain rule, again, we're being asked to take the derivative. But now we're not taking the derivative of a fraction or two functions being multiplied by each other. We're taking the derivative of a function, which is g, inside of another function, which is f. What does the chain rule say? Well, the chain rule says this. What we need to do is take the derivative of f, which is the outer function. And I'm going to go ahead and translate this into words for you. We're going to take the derivative of the outside function. Again, that outside function, outer function is f. And then we're going to leave the inside function alone. You'll see this better in some examples, but I just want to go over this idea for now. So again, we're going to take the derivative of the outside function, which is f, and we're going to leave that inside function alone. Maybe that makes a little bit of sense if you recall the last slide. Then what do we need to do? We need to multiply by the derivative of the inside function. And again, hopefully you remember that from the last slide. We multiplied by 6x on that last slide. So the very end of this process called the chain rule is to multiply by the derivative of the inside function. Okay, so what does that bring us to? Well, it brings us to a extension, a logical extension of the chain rule, and it's just a special case of the chain rule, which we call the general power rule. Not all composite functions are the same, but what if we have a composite function where we have something to the nth power? Not an x to the nth power, but some stuff to a power. Kind of like the example above. We have some stuff, x squared plus 1, to a power, which is 3. Well, this is when we can call on what is a special case of the chain rule, and that's going to be the general power rule. So what does the general power rule say? Well, it says something that you guys should all kind of recognize, which kind of looks like the power rule. The general power rule, or this special case of the chain rule, tells us to take the power, bring it down to the front. We're all used to doing that step. Then what we're going to do is rewrite the inner function. In the past, that was just an x. In these types of problems, it's going to be, for example, like x squared plus 1 that you see above. So we're going to rewrite that inner function, subtract 1 from the exponent. So that's kind of been what we've learned up until now. We know how to do the regular power rule, so this is the exact same process until you get to this last step. In this last step, we have to multiply by the derivative of the inner function. And that completes the general power rule, which again is just a special case of the chain rule. So both of these versions we're going to use. It just depends on what kind of problem we're looking at. So don't focus on one over another too much, because both are going to be used just as much. Now let's see the chain rule in action. So something to realize, we've actually been using the chain rule all along. If you take a look at this first formula up here, that's our regular power rule. When we have a regular or a plain x to a power, we bring the power down, we rewrite the x, and we reduce 1 from the power. We've been practicing that for a while now. But now we have this new thing called the chain rule here. What does the chain rule say? Well, it's basically the same process, but now we don't have a plain x to a power. We have something which we call u to a power. It's still basically the same process. We bring down the power, we're going to rewrite the u, reduce 1 from the power, but now the big difference is we're multiplying by the derivative of that u, whatever that inner function is. So instead of starting with a true, chain rule problem, let's start off with a problem we know how to do already, just to prove that we've been using the chain rule all along. So what's the derivative of x to the 6th? Well, we can do that very quickly. We know that's 6x to the 5th. But let's apply this process of using the chain rule and see how that looks. So it's going to feel weird to do, but what I'm going to do is I'm going to make this little box off to the side. I guess I'll call it our u box. And what I'm going to do is I'm going to call u x. The reason I want to do that is so I can get it to look like my chain rule formula, which you see right here. We need a letter u to a power, so I'm going to go ahead and call u x so that it looks like that. So now let's go ahead and apply the process of the chain rule. What we're going to do first is bring down the power of 6, so we're going to write our derivative notation, f prime of x, bring down our power of 6, rewrite u just like the formula shows, reduce the power by 1, but now we're going to multiply by the derivative of u. I'm going to do this off to the side in this what I again called u box. What does u prime equal? Well, if you're focusing on this u box right here for a moment, star it. If you focus on that for a moment, the derivative of u is u prime. The derivative of x is 1. So we know u prime is equal to 1. So we can go ahead and add that into our derivative. U prime, which we need to multiply by, is 1. So how can we clean this up? Well, of course, multiplying by 1 doesn't change the problem. So we have 6. If you recall from our little u box on the side, we called u x, so we can plug that back in. And when you plug that back in, we get the answer we already knew. The derivative of x to the 6th is 6x to the 5th. All I did was I applied this longer process, so to speak, of the chain rule. Because the point is this, we need to always use the chain rule when we're taking derivatives. It's just in cases when we have a plain x to a power, we don't need to really use the chain rule because we know we're going to end up multiplying by 1 at the end. So we can just take the derivative like we did since 2.2 and again use our regular power rule. Okay, so let's take a look at a problem that we do need the chain rule for. F of x equals x squared plus 1 to the 3rd power. How do I know that this is a chain rule problem, other than the fact that I said we should always be thinking about using the chain rule? Well, I see a function inside of another function. I see x squared plus 1, which is one function, all raised to the 3rd power, which is a different function. And since it's not a plain x to a power, we need to apply the chain rule. So I'm going to always draw this little u box off to the side to show that work, to kind of keep track of what we're doing. So I'm going to go ahead and call u x squared plus 1. So we can rewrite our function. Again, we haven't taken a derivative here. All I'm doing is I'm rewriting the function as something, as a u, the something, to a power, just like above, just like what the chain rule needs us to have it written as. Okay, so now we can apply the process of this chain rule, and I've just copied it here just so we can kind of reference it a little bit easier, but here's our chain rule again. So what's it say? It says we need to bring down the power of 3. We need to rewrite the u, leave that u alone, don't touch it. Take that power and reduce it by 1. And now we need to multiply by the derivative of u. Over in our u box over here, again I'll start to make sure you're looking over here. Our u box shows that u is equal to x squared plus 1. What would u prime be equal to? Well, the derivative of u is u prime. The derivative of x squared plus 1 is 2x. So we know u prime is equal to 2x. So we need to multiply by 2x. This step right here shows you know the chain rule. Other than cleaning it up and simplifying, that is the chain rule. So how can we clean this up and make it look a little bit better? Well, we can move the 2x to the front with the 3. So 3 times 2 is 6. And then we don't really want to leave this u in our final answer since we know u is equal to x squared plus 1. So just make that little note over here. Always remember to multiply by the derivative of that inner function. Again, we call that u prime. So when we clean this up, again, we'll bring the 2x to the front. Becomes 6x when we multiply. We're going to plug the u back in. We don't want to leave that u there, so we're going to replace it back again with x squared plus 1, and then the power is 2. Okay, continuing along with more chain rule problems. So kind of complicated looking problem. So what should we do? Well, at least in this course, every time we see a root, we really want to replace that with a power. And if we take that cubic root and replace it with a power, and in addition we have this square in here, all of that is going to become a 2/3 power. The third root becomes a 3 in the bottom of the fraction, and since it's a function being squared inside there, that 2 will go to the top of the fraction. So we can rewrite our function as x squared minus 1 to the 2/3 power. How do I know this is a chain rule problem? Well, I see a function inside of another function. Our inner function is x squared minus 1, and that's all being raised to the 2/3 power. If we have a function inside of a function, we need to get that function that's inside out of there. In other words, we need to call it u. So we're going to draw our little u box over here to the side, and of course call u x squared minus 1. So what does our function become? Well, instead of x squared minus 1 to the 2/3, it's now just u to the 2/3. Once we have that u to a power, we know how to take the derivative. We're going to use the chain rule. And I've copied it again here just for our reference so we can follow the steps of the chain rule. So let's go ahead and do that. What is f prime equal to? What is our derivative equal to? Well, we need to take our power, bring it down to the front, rewrite the u, don't touch the u, don't change the u, it's exactly like the formula, reduce the power by 1. Now we need to multiply by u prime, which is where we need to come back to our little u box over here that I'm starring. We need to come back to the u box and find u prime. Luckily, that's pretty simple. Our u is x squared minus 1, which makes u prime 2x. So we need to multiply by 2x at the end of the line. Just like that last example I did, this step right here shows that you know the process of using the chain rule. Other than simplifying and cleaning up this answer, that is the answer. Okay, so this u prime at the end, we usually want to bring to the front just to kind of clean things up a bit. So if you bring the 2x to the front with the 2/3, we're going to end up with 4/3 x. Remember, we really don't want to leave that u in our final answer because we know u is equal to x squared minus 1. That's what we called u. So we're going to rewrite the u, but accept as x squared minus 1, and then 2/3 minus 1 as the power is negative 1/3. If need be, you could rewrite this answer if you needed a positive exponent by taking it and moving it to the bottom of a fraction. That 3 in the bottom is from our 4/3. Okay, next example. I think this is where the chain rule can kind of get disguised a little bit. We have a fraction, and if you kind of get a little too used to using the chain rule right away when you see a fraction, you might not realize that this is really not a quotient rule. Mainly because we don't have a function over a function. We have a constant over a function. And we can take a step to go ahead and rewrite that and maybe make this problem a little bit easier than going through the chain rule process. I'm sorry, the quotient rule process. So how could we rewrite this as not a fraction? Well, just like in the example above in the answer, we can take that thing out of the denominator and move it to the top of the fraction with the -7. All we need to do is make the sign opposite. It's a +2, so that would become a -2. And now this is a really great candidate for the chain rule. I see a function, 2x minus 3, inside of another function, which is something to a -2 power. I see a function inside a function, so we can go ahead and get that function of 2x minus 3 out of there. If I replace 2x minus 3 with a u, our equation becomes a little bit simpler to look at. It's just -7 u to the -2. Since I have a u to a power, not a plain x, but a u to a power, I can apply the chain rule. And again, I've brought it up again just so we can see it in terms of its process. So what does the chain rule say? Well, what we need to do is bring the power down to the front. But since we already have that -7 there, I need to rewrite it, kind of just let it sit there so that we can apply the process of the chain rule. So we'll bring the power down, -2. We're going to leave that u alone. Don't change it, don't alter it. We're just going to rewrite it, reduce the power by 1, and then multiply by u prime. In this case, in our u box, you'll notice u prime is just equal to 2. So we need to multiply by u prime, which is just a 2. Again, this step right here shows you know the process of the chain rule. Other than cleaning this thing up to make a nice looking answer, that shows you know the chain rule. So like I said, that u prime you really want to sometimes bring to the front to kind of clean things up. So the -7 times -2 is 14, times 2 would be 28. Again, we don't really leave the u in our final answer, so we're going to take the u and replace it back again with 2x minus 3. And again, we need to subtract 1 from the power, so -2 minus 1 is -3. Just like above, if need be, you can rewrite this answer with a positive exponent. Since we have a negative power, we can make it positive by sending it to the bottom of a fraction. So the 28 stays in the top, and we'll send the 2x minus 3 to the positive third power down to the bottom. This next problem is a hopefully very, very common problem for you by now. We're being asked to find an equation of a tangent line. Like you've heard me say in the past, every time you see a problem mentioning something about an equation of a tangent line that you need to write, the very first thing I would write down is our point-slope formula, because that's what's going to get us to the answer. We need a point and we need a slope. So how are we going to do this problem? Well, we want to find the equation of a tangent line at the point given, which is 3, 4. This is our x. This is our y. So we have those two values already. We're halfway there. We have our point. Now we just need our slope. Anytime we think or hear or see the word slope, I hope you're thinking derivative. So that's what we need to do. We need to take our function and find the derivative. So again, like previous example you saw earlier, we don't like square roots or cubic roots or fourth roots written that way. We would rather have them written as powers. And you'll notice when we rewrite this function, we have a composite function. We have a function inside of another function. We have 25 minus x squared that is inside our square root, which I rewrote as a 1/2 power. This should hopefully inspire you to now think of using the chain rule and our little U-box process. So off to the side, I'm going to draw my little U-box. I'm going to get the 25 minus x squared out of my function and replace it with a U. As soon as you realize this is our chain rule kind of problem, we can think about that process of using the chain rule. So what did the process of the chain rule need us to do? Well, we need to take the power, bring it down to the front. We need to rewrite the u, leave it alone, don't change it in any way. Take that power, reduce it by 1. And if you don't make the common mistake, which is to forget about multiplying by u prime, you'll need to come over to our u box again over here, which I want to illustrate or point out with a star. We need to find u prime. If I take the derivative of u, which is 25 minus x squared, we'll get negative 2x. Which is what we need to multiply to finalize that process. Again, this step right here shows you know the process and procedure of doing the chain rule. Other than simplifying and cleaning things up a little bit, you're ready to go after this. So that u prime term I always like to bring to the front to kind of help simplify things. The 1/2 and the 2 will kind of cancel each other out, so we'll be left with negative x. Again, we don't leave that u there, so I'm going to rewrite that as 25 minus x squared, and then we reduce the power by 1, which gives us a negative half. So what do we need to do now? Well, in past examples, that's kind of it. We stopped right there because the point was just to find the derivative. But the point of this problem is to find an equation of a tangent line. So we need the slope at the point 3, 4. So what do we need to do? Well, I think it would be helpful in this case, since we need to evaluate our derivative, to, like you've seen me do in the past, simplify our derivative. Since we have a negative 1/2 in our power, we can send that down to the bottom of a fraction as a positive 1/2 power. But instead of writing it as a positive 1/2 power, we can change that back to a square root. So our derivative is really equal to negative x over the square root of 25 minus x squared. So this is our derivative, or the version of the derivative we want to use to now find the slope at x equals 3. To find the slope at x equals 3, we need to take the value of 3 and plug it into our derivative right here. We're taking this value of 3 and plugging it in to our derivative. When you plug in 3 into that expression, you'll find that the slope turns out to be negative 3/4. After that, all you need to do is plug in everything you know. We know y is 4. We know our slope is negative 3/4. We know our x value is 3. And just like you've heard me say in past examples, on the AP test, specifically the free response section, that is a perfectly acceptable answer, and you can leave it like that. I'm just going to simplify it for the sake of giving you the practice of seeing it simplified, but that is a perfectly acceptable answer on the free response section. If this happens to be a multiple choice kind of question, you might need to simplify it to get it down to the point of an answer choice. So in this case, when you simplify the equation of a tangent line, you get negative 3/4 x plus 25 over 4. In this slide, we're going to take a look at trig functions with the chain rule. So this little table, this box here, you guys have printed in your notes already from before, and we saw it in 2.3. The only difference with the table from the version in 2.3 is now we've applied the chain rule to our trig functions. And again, like I mentioned before, you only need these 3 on the left memorized. The 3 on the right, rarely used, so we're not going to dedicate those to memory. So how have these formulas changed from when you saw them from before? Well, the only difference you'll notice is now at the end of each of them, we're multiplying by u prime. Why is there a u prime there? Well, now sine is not sine of x, it's sine of u. In other words, there's some other stuff inside the sine function, which we'll take a look at a few examples in a moment. So keep that in mind. If you see a function inside of a function, sine would be the outer function, u would be the inner function, we need to apply the chain rule, which means ultimately we need to multiply by u prime. So let's take a look at our first example. We're going to take the derivative of cosine 4x squared plus 5. How come we can't take the derivative right away? Well, it's not cosine of x, it's not a plane x. So since it's not a plane x, we need to get that inner function out of there by calling it u. And again, I'm going to draw our little u box here so that we can kind of keep track of what's going on. So are we really taking the derivative of cosine 4x squared plus 5? No, we're really taking the derivative of cosine u, which we know how to do. The derivative of cosine u, you can see right here. It's not something you need to kind of think of in terms of a process, you just have to have it memorized. So what is the derivative of cosine u? Well, the derivative of cosine u, you can just copy. It's negative sine u times u prime. And that's it. It's almost too easy, assuming you know what the derivative of cosine u is. All we need to do now is figure out what u prime is. U prime, we can go back to our u box here and take the derivative of u. The derivative of u in this case is 8x. So how can we finalize this answer, well, we can just take everything and plug it in. Sine u is now going to become negative sine u will now become negative sine 4x squared plus 5. We're going to plug that u back in. And through our u box, we found that u prime is equal to 8x. Like you heard me say in the previous examples, there's nothing wrong with writing this out as your final answer, but it's usually better to bring that u prime to the front to kind of clean things up. So I'm going to go ahead and do that. I'm going to pull the 8x to the front, so that'll become negative 8x sine 4x squared plus 5. Now a little harder problem. In this example, we're going to use the chain rule a couple different times here. But before we get to why that's the case, the very first thing I'll ask you to always do when you're doing trig problems that have a power is to rewrite those trig problems. It gets a little confusing, if not totally unrecognizable, to leave the power of 3 next to the SIN or the COS or the TAN. A better way to rewrite these trig functions, if they are to a power, is with parentheses. So that's what I'm going to do. Sine 4x to the third power. So we have a function which is sine 4x inside of another function which is a power of 3. As soon as you realize we have a function inside of another function, I hope you're thinking about using the chain rule. So what do I want to do? Well, we need to take that sine 4x, that inner function, and get it out of there by calling it u. And that's great, because when you do that, it just becomes u to the third power, which we know how to take the derivative of. We know by the chain rule, which again you see right here, this is our chain rule, we're just going to apply the process of the chain rule. So when we have u to the third power, we'll bring the power down, leave the u alone, don't mess with it, don't alter it, reduce the power by 1, but now we need to find u prime. So at the beginning of this problem, I said it was going to be a repeated use of the chain rule. We've already used the chain rule once right here, and you see it with our little formula, but why are we going to need the chain rule again? Well, you'll notice over in our u box, since we need to find u prime, we have another composite function. It's not a plain x inside of the sine function, it's a 4x, and that's not a problem. We can see up in the table here that the derivative of sine is cosine, but then we need to multiply by u prime. So what's that going to look like in this case? Well, the derivative of sine 4x is cosine 4x. So not too bad, but because that 4x is present, it's not a plain x, we need to multiply by the derivative of u. You see it right here, we can't forget about u prime. The derivative of 4x is 4. So this is definitely a much more difficult problem because we're using the chain rule a couple times. But once we get to that point, we can take u prime, plug it in, and like I've said before, that shows you know the process of the chain rule. Of course, we're going to simplify and clean it up, but that's kind of the important step. Okay, so this 4 that you see at the very end of the line, I'm going to pull to the front with the 3, which will be 4 times 3, and that's 12. We're going to again replace that u with what u is, sine 4x. 3 minus 1 is a power of 2, and then we have the cosine of 4x at the end. This next example will kind of be an illustration of a problem that usually gives Cal students some issues. It's a problem that involves a conceptual use of the differentiation rules we've been looking at for these past few sections. So all we're going to be given here is a bunch of values in a table, and we need to find some derivatives. So let's jump right into it. The first example, or first problem we need to work here is what is the derivative of f of x times g of x at x equals 1? So let's kind of ignore this table for a moment because we need to take the derivative of f of x times g of x. Well, we don't know what those functions are, and that's okay. We just need to know the process of taking those derivatives. So what do we do when we have two functions being multiplied and we need to find their derivative? Well, we apply the product rule. And without going over the details in a slow process here, I'll have you refer back to the product rule, but we'll end up with this result. The derivative of the first times the second plus the first times the derivative of the second. So straight out of the definition of the product rule. And after that, we just need to evaluate that at 1, which means plug in 1 for x. And again, I'm putting these brackets around here just to kind of make this a little bit simpler to see that it's really just two numbers we're adding. So going over to our table here, we can look up these numbers. F prime of 1 is 3, g of 1 is 2. I'm sorry, f prime of 1 is 0 actually, if you look at the table, and g of 1 is 2. F of 1, and I'm going to box that or put brackets around that real quick. F of 1, if you look in the table, is 3. G prime of 1 is 3/4. And again, we're going to multiply those two and add the two numbers together. Of course, 0 times 2 is 0. 3 times 3/4 is 9/4. So a little bit more difficult, but in some sense a little bit easier because we're not dealing with real functions. We're just dealing with the concept of how we apply derivative rules. What about g of x over f of x? Find that derivative and plug in 1 after that. Well, we have a function divided by another function. Hopefully that inspires you to remember our good old quotient rule. Low d high minus high d low over low low. So again, without going over the tiny details again of that whole process, you see the result of applying the quotient rule. Low f of x times d high g prime of x minus high g of x times d low f of x. Low d high minus high d low over low low, which is the bottom squared. After that, we can plug in our x value. Our x value here is 1, so again, just to kind of help out the arithmetic here, I'm going to put brackets around the two numbers we're subtracting in the numerator. When you look up all the numbers and plug those in, you'll end up with 3 times 3/4 minus 2 times 0, all divided by 3 squared. 3 times 3/4 is 9/4, minus 0 is just still 9/4. We're going to divide 9/4 by 3 squared, which is 9, or a final result of 1/4. Next example, we have a function which is a composite function. We have our function f, and inside of f is g of x, f of g of x, and we want to take that derivative and evaluate it at 1. Well, now we can use the chain rule that we learned in this lesson. The derivative of f of g of x is the derivative of the outside function, which is f prime, and we leave the inner function alone, which is g of x, and then we multiply by the derivative of the inner function, which is g prime of x. Again, a conceptual application, since we don't know what these functions are. After that, all we need to do is plug in our x value of 1. So we're going to have f prime of g of 1 times g prime of 1. The first number we got to look up is g of 1 and g prime of 1. G of 1 is 2, g prime of 1 is 3/4. Now we need to look up a second number. Now we have f prime of 2. F prime of 2 is 1/3 from the table, and we're going to multiply that by 3/4. Once you multiply those, the 3's will reduce out, and we're left with an answer of 1/4. Last example is a very important example because it's going to illustrate a couple concepts that usually Cal students first learning these ideas kind of get tripped up on. The first is this. The way this is written is a little bit weird. We have an f with the third power and then parentheses x. What that's really saying is we're taking the function f and cubing it. It's not a real good way to write it, so I'm going to rewrite it in a clear format. Instead, I'm going to put f of x inside the brackets to the third power. And then it becomes a little more apparent what we need to do here. We have a function inside of another function. We have a f of x, which is inside a cubic function. So when we have a function inside of another function, we should be thinking chain rule. So what does the chain rule look like when you apply it? Well, think about the process of the chain rule. It says to bring the power down, which is why we have a 3 here. We're going to leave that u alone, which is the f of x, the inner function we leave alone. We reduce the power by 1, which is 2. But here's the all-important part. We need to multiply by the derivative of the inner function, which is f prime of x. Once you complete that process, The rest is just a matter of plugging in the x value in question. Here it's 2, unlike the previous 3 examples. So f of 2, if we look it up in the table, is 7. F prime of 2 is 1/3. And you'll notice we have a 3 and a 3 that can cancel here. So 7 squared is 49.